So again, one of the reasons we started with a warm-up looking at cubes is because we are going to look at some more special factoring patterns today. And the first one that we're going to look at are the sum and difference of two cubes. Okay. Froze again. Okay. All right, so the sum of two cubes, we've got a cubed plus b cubed is equal to, and then it factors into a plus b, and a squared minus ab plus b squared. And the difference of two cubes is a cubed minus b cubed, and that factors into a minus b times a squared plus ab plus b squared. Do you recognize any kind of pattern between those two? Switch the signs, okay? So the a and the b, those parts are exactly the same. That first binomial factorization follows the sign of the original binomial. And then you'll notice the second part, the trinomial, the first term is always squared. The second term is always the first times the second, and the third term is always the second term squared. Okay, and because even if you have a negative value and you square it, it's always positive. So that last term will always be positive. All right, so just sort of pay attention to the patterns here. So we're going to go ahead and apply it in our first one. So again, when I see the first one, I've got this x cubed plus 8. I notice right away I have a cube, okay? And then that's going to prompt me to look at the other term and see, wait, I have 8, which is nothing but what cubed? It's 2 cubed. So I'd say, okay, this is a difference of, sum of 2 cubes. So I can take the cube root of each of those terms. So the cube root of x cubed would just be x, and then as we said, the cube root of 8 is just 2. And then I'm just going to plug it into that pattern that we talked about. Because it is a plus, the first factorization is going to become x plus 2. And then the second part, the first term squared, so this becomes x squared. The sign flips for the next one. The next term is the a times the b term, so that would be 2x. And then again, the last term is always positive, and it's the last term squared, and it would be 2 squared, which is 4. And there's the factorization. All right. Does anybody look at that trinomial and is tempted to try to factor it? Okay. Question?
So on the difference of two cubes, you're getting how it says a cubed minus b cubed. Then why is it just x when you did x plus 2?
On this part here?
Yeah.
Okay, so it's like if you look at the form here, this a is gonna, it's just a single a to the first power. So you take the cube root of that first term. Yes?
Can we leave it as x plus 2?
Are you saying, can you leave it as this?
Yeah.
It's not the same thing. This is a very common mistake. No, it is not the same thing. Okay. All right. And I started to ask the question earlier, does anybody look at that trinomial piece and feel like you could factor it further? Please remember that if you start with a sum or difference of two cubes, that trinomial piece, if you did it correctly, will not be factorable again. Okay. So if you end up with the trinomial there and you can factor it, then something went wrong in your initial factorization. Okay, this will not factor. All right, so let's look at the next one. Okay. I have 8x cubed minus 27. So again, I would notice, well, I have a cube there, but it has a coefficient. But as we saw in the previous example, 8 is a perfect cube of 2. All right, and then I'm going to look at the 27, which we notice is perfect cube of what? 3. All right, so again, I'm going to look at what is the cube root of 8x cubed. That will be my A term. So that'll be 2x. And my B term is going to be the cube root of 27, which is 3. And again, just going to apply the form that we know, the pattern here. So it's the first term, so that'll be 2x. And because it is a difference, this first sign will be a minus, and then our B term is 3. And then we multiply that by, again, it's the first term being squared, and what we have to remember is now I have a coefficient attached, so it's actually all of 2x that's going to get squared. The sign changes. Since we started with the minus, this one will be a plus, and we multiply A times B. So my A is 2x, my B is 3, and then plus B squared, so 3 squared. So now I just want to go ahead and simplify things further. 2x minus 3 just carries down. And how do we simplify that 2x, the whole thing being squared? 4x squared. So this is 4x squared plus 2x times 3 is 6x, and 3 squared is 9, and that is the final factorization. And again, don't be tempted to factor that trinomial further, because it is not factorable. Okay. Alrighty. Are we ready for our next one? Okay, so our next one is factor by grouping. Okay, and we look at this, and usually when you see 4 terms like this or 6 terms, that's when we want to be thinking about factor by grouping. This should already be familiar to you because what you guys call rooftop method, or when we split the middle term, it's the same process. Okay, except this is, you kind of think of this as it's already been split for you. Okay, so usually when I see a group of 4 like this, that's the first thing I think of. How can we group this? All right, so I'm just going to go in the order that it's already put in place. I'm going to group those 2, and I'm going to group these 2. And then looking at the first group, what can we factor out of 12x cubed and 4x squared? 4x squared. So 4x squared comes out, and that's going to leave me with 3x here plus 1. And we already have 3x plus 1. Okay. So I'm going to just go ahead and factor a 1 out, just as sort of like a placeholder to remind me that I'm still factoring. Okay, so now I have 3x plus 1 in 2 places, so I know I can factor that out. And I'm left over with the 4x squared plus 1. So I'm going to put the 4x squared plus 1 first, since it has a higher degree. And 3x plus 1. Okay. And then we would want to look at those and see, can these, either one of those be factored any further? No. So there is our final factorization. So our next one, 2n cubed plus 5n squared plus 6n plus 15. Again, I'm going to look at that and say, well, I've got 4 terms. I'm going to go ahead and try factor by grouping. and see if it works. So again, just going in order, I group those two and those two. All right. Then looking at our first group, what can we factor out of that one?
2n².
Can we get a 2 out also? No, just n squared. And that'll leave me with 2n plus 5. And what can be factored out of the second group?
3.
A 3. And that'll leave me with 2n plus 5. And then we can see, okay, this one does work, factor by grouping. And I'll factor out that 2n plus 5 so that I have n squared plus 3 times 2n plus 5 left. And can either of those be factored any further? No. So we are finished with that one. Any questions so far? All right. Okay, so this next type of factoring is what happens when we have a polynomial that happens to be in quadratic form. Okay, basically meaning the quadratic or the polynomial, it has higher degrees, but we can use the rules of factoring quadratics to factor the higher degree ones. Okay, so when I look at this one here, I see that I've got 3 terms. And the first term is an x to the 4th. And the middle term has half the degrees of the first one. Okay. So if you see that this is one of those that you should be thinking, oh, I can probably treat this like a quadratic. So when you're first starting with these, it's sometimes helpful to do like a little substitution thing with it to make it look more familiar. Okay, so I'm going to substitute here. I'm just going to use the letter a, and I'm going to let a equal x squared. Okay, so if I come back and substitute the a's into my trinomial there, x to the 4th would become a squared. Okay, minus 8, and my x squared would just become a plus 15. Now, is that a trinomial that we can factor easily? Yeah. What does this factor into? -5 and -3. And then the only thing you have to remember is a was not part of the original polynomial, so I need to replace the x squared back. Okay, so I just come back and I'm going to do x squared minus 5 and x squared minus 3. And again, I want to look, can either of those be factored any further? No. So that is the final factorization. We ready for the next one? Yes? No? Okay. So 5x to the 4th minus 9x squared plus 4. Right. So again, I see that it is a trinomial, and I see that I have a 4th degree in the first position, and my middle term is exactly half the degrees. So again, it'll fit the pattern of a quadratic, so I'm going to do the same thing. I'm going to use a different letter this time. I'm going to let b equal x squared. So when I come over here, this is going to become 5b squared minus 9b plus 4. And is that something we can factor fairly easily? Yeah. Okay, so this one, you could do the split the middle term if you wanted, but also we can recognize that 5 only has 2 factors, so 1 and 5. So this makes it a little bit easier to solve this part. So it has to be 5b and 5, or sorry, and b. Okay, 4 doesn't have that many factor pairs either. So what combination would work here? Okay, so if we do -4 and -1. And then we want to keep in mind that x squared was the original variable, so I need to substitute that back into place. So this is 5x squared minus 4, and this is x squared minus 1. And again, I want to look at these two. Can either of those be factored any further?
Yeah.
Yes. Which one?
The first
Is it the first one?
No,
The second one. What is that second one?
the difference of two.
Difference of 2 squares. So what does it factor into? And x plus 1. Okay. So the first term we're just going to carry down, but we notice the difference of 2 squares, so we factor that one out further. And now it is fully factored. Okay. Questions so far? Okay. All right. So this next part is what we call the factor theorem. And the factor theorem says that if you have this polynomial, f of x, and x minus k is a factor, it'll be a factor if and only if f of k is equal to 0. So meaning you would plug that value in, and if the polynomial equals 0, then you know it's a factor. So this can be a quick test. Okay, so determine whether x minus 3 is a factor of x squared plus x minus 12. So if the factor is x minus 3, then that means x would equal 3. And that's what we're going to plug into the equation and solve. So f of 3 is equal to 3 squared plus 3 minus 12. So this would give us 9 plus 3 minus 12, which is equal to 0. So since that is equal to 0, then we know that x minus 3 is a factor. Okay. So the next one, we want to show that x minus 6 is a factor of f of x equals x cubed minus 5x squared minus 6. Sorry, 6x. So again, I could apply the factor theorem and try plugging it in. So again, if the factor is x minus 6, that means x is equal to 6. And I go to plug this in, and I get 6 cubed minus 5 times 6 squared minus 6 times 6. Okay, so I'm looking at that and I'm like, ugh, 6 cubed? Or how about 36 times 5? Okay, these are kind of larger numbers that I would prefer not to have to do, because I'd have to do the multiplication out on the side. So, what is another quick way we could check without using factor theorem? Okay, we can actually factor out the x minus 6. Oh, are you talking about factoring this part? Or?
Like you do what you did before, and then you see like x minus 6
is one of those. Okay, and I'm thinking another really quick way. Okay, a factor is just a form of what operation? Division. Can we divide pretty easily by x minus 6? Yes, using what method? Synthetic division. So very quick to do this as well. I can plug in my 6 here in the corner. I have a 1x cubed, negative 5x squared, negative 6x. I don't have a constant, so I'm going to fill in a 0 for there. And this is going to become pretty quick. Carry my 1. 1 times 6 is 6. 6 minus 5 is 1. 1 times 6 is 6. Negative 6 plus 6 is 0. 0 times 6 is 0. And how do we know that that's a factor?
There's no remainder.
There's no remainder. Exactly. So remainder equals 0. Therefore, x minus 6 is a factor. So again, those are 2 ways that you can check. And again, it just depends on the numbers. The first one, using the factor theorem, was really quick. The second one, that synthetic division, to me was a lot faster than doing all that long multiplication. Oh, I don't know. Maybe you prefer the long multiplication. I don't particularly. Okay, so any questions on what we've done? Alrighty, so I know that everybody likes to work on your notebooks, but I'm going to ask you to get up, work with partners or in groups of 3, and go up on the board. These require factorization. There's a little bit more to them than the ones we just did in class together. Okay. Right. Okay, so B seems to be the one that most of you had the most trouble with. And so I started with that hint. Working with negative leads, just through my own experience, has always made things more complicated. I know some of you just factored the negative 1 out. If you do that, it means you still have that negative looming in the front. So if you can rearrange, that's normally what I would suggest. So I started by turning this into 625 minus 6n to the 4th. Okay, the rest of it was a little bit difficult to see. So 16, we can recognize that as a square. What we want to notice, it's a 4th degree. So if it can be halved into an integer value, then you know it's a perfect square also. All right, so, and then 625, that one was the little bit larger one. If it ends in 5, we know that it has to be made up of 5s. We know it can't be 5 squared. So the next thing would be like, is it 15 squared? Now it turns out it's 25 squared. So again, difference of 2 perfect squares means that we would have to split this up. So remember, a squared minus b squared is a plus b, a minus b. Okay, so this becomes 25 plus 4n squared and 25 minus 4n squared. And then we would want to notice that we have another difference of perfect squares. So don't forget this one. This piece doesn't go away. We can't factor it further, but we have to carry it down. And then we factor the next one into the 5 plus 2n and 5 minus 2n. That one was lots of fun, wasn't it?
I had a great time.
You had a great time?
Factor out the first.
It's a sum of squares, which is not factorable. Right. Okay, it seemed like you guys did fine on the rest of them. Not so bad? Okay. This one here. On this one, it's a show that x plus 3 is a factor of this long polynomial, and then factor it completely. So if you're told that to show that it's a factor and you still need to factor it, what technique would you want to start with?
Just factor it, and then once you have the factors, we say x plus 3 is one of the factors.
Yes, right. So I wouldn't spend time plugging in -3 and finding if it equals 0, because if we factor it, we are already going to know. What is a quick way to factor this also? Not necessarily group. What did we do earlier?
Divide by x plus 3.
Divide by x plus 3, because this one can be done very quickly using what method? Synthetic division makes this really quick, right? So if we do this -3 in here, I have a 1x to the 4th, 3x cubed. I don't have an x squared term. My x term is -1 and -3. And so again, we can do this really quickly. Carry the 1, there's -3. I get 0, that's 0, 0. And then I get 0 again here, -1. And then -3 times -1 is +3. I'm zeroed out. Okay, and again, that's evidence that this is a factor. So again, we know remainder equals 0, therefore x plus 3 is a factor. And because we chose to do it this way, we already can see what the other equation is. So that's the remainder. This is, remember, the x to the 0 term. That's the first, second. This one is an x cubed term. So right now we are factored into x plus 3 and x cubed minus 1. But is there anything we recognize there?
A difference of perfect cubes.
Difference of perfect cubes. And so we would have to go a step further in this one. And so x plus 3 we can't do anything with. It's going to carry. And then our difference of perfect cubes would become x minus 1 times x squared times x plus 1. And there is the final factorization. So keep in mind there's more than one way to test to see if something is a factor, and just do the most efficient way. If it's efficient to plug in the value and evaluate it to see if it equals 0, then do it that way. If it's quicker to do a little quick synthetic division, then do it that way. Right? Just do the method that's going to be quick. Yeah, I'm already looking at this. I don't want to do -3 to the 4th power. Okay, so this last part we just have a couple application problems.
Yay.
Yay! Everybody's favorite, right? Okay, so we've got this box here, and it tells you that the volume is represented by this nice, long, fun equation here. And it's asking us to find the binomial that represents the missing side. Okay, so let's say this was the length. We'll say this one is the width, and this one is the height. Okay, and so again, we know that the volume of a box is length times width times height. All right. So for us, again, the length, that's the unknown piece that we don't know at the moment. So I'll do this. The width is x plus 4. The height is x plus 2. And we know that the whole entire volume is equal to this nice long equation here. 2x cubed plus 17x squared plus 46x plus 40. Okay, what is our goal here? Find the length. Okay, how am I going to get length alone right now? We're going to divide the width and the height out. Okay, so again, dividing both sides by this and by this. Does that look like it's not going to be much fun?
Yeah.
Okay. But can we make this easy on ourselves?
I hope so.
Okay. Do we have to divide out both of those binomials together at the same time?
No.
No. We can do one at a time using, what's our nice quick method? Synthetic division, right? Okay, so do you guys want to start with the 4 or the 2?
The 2.
You want to start with 4? Okay. So, since it's x plus 4, that means we put a negative 4 in our box, and we just fill in our terms. We have a 2x cubed, a 17x squared, a 46x, and a 40. All right. Carry the 2. 2 times negative 4 is negative 8. 17 minus 8 is 9. 9 times negative 4 is negative 36. 46 minus 36 is 10. 10 times negative 4 is negative 40. Did we expect to zero out at the end? Yes, because we already knew that it was a factor of this. Okay. What's the equation we have left over here?
2x squared plus 9x plus 10.
10. Okay, and I want to divide that by
X plus 2.
the x plus 2. So we get a negative 2 in here, and we have 2, 9, 10. And so we can very quickly carry that 2 times negative 2 is negative 4. That's 5 times negative 2 is negative 10. 0. What is the length of our missing side?
2x minus 5.
2x plus 5. Okay. So, did that problem look pretty rough to begin with?
Yeah.
But was it?
No,
No,
it was not.
it was not. All right. Okay, last application. We are designing a rectangular swimming pool to be set into the ground. The width of the pool is 5 feet more than the depth, and the length is 35 feet more than the depth. The pool holds 2,000 cubic feet of water. What are the dimensions of the pool? So where is it we should start with this? Yes, draw a picture, okay? That always makes things so much clearer. All right, it's a rectangular swimming pool. So, and it has a depth to it. All right, so I'll call this my length here. That's my depth, and I'll call this my width. Okay, and it says the width is 5 more than the depth. So D plus 5. The length is 35 more than the depth. So D plus 35. And it holds 2,000 cubic feet. So again, we know that the volume is equal to the length times the width times the depth. Why didn't my L come? Okay, there we go. All right. So the volume is supposed to be 2,000 equal to, and then we have D plus 35, D plus 5 times D. And again, what is our goal? What are we trying to find?
D.
Right now, D, because that's the only variable we have in there. So what would I have to do?
Divided by
Subtract
D
2,000.
plus J.
Huh?
D
I
plus
t-
J.
Well,
Subtract by 2,000.
Okay.
Or like do their minus something.
not factor it, but
Like multiply it out.
we need to multiply it all out, right? Because remember, once we're factored, the only time we can solve is if it's equal to 0. Right now we are not equal to 0. So that means I'm going to have to distribute all of these terms out. Okay, so we get 2,000. And is it looking like this is going to be horrible? Kind of to start, but we'll work through. So we get d squared plus 5d plus 35d plus, that's 175, all times d. Okay. And so now I have 2,000 is equal to d cubed. If I combine 5d and 35d, that's 40d times d. So that's 40d squared. And then plus 175d. And again, we have to have it equal to 0 before we can do anything more. So I'm going to have to subtract the 2,000 from both sides. So we get 0 over here minus 2,000. All right, so at this point, I'd be like, oh, I have 4 terms. I'm going to try factor by grouping. Okay, I'll go ahead and tell you, factor by grouping does not work with this one.
Is there a way we can note that it doesn't without actually?
Yeah, you would start it, and then the second you made your 2 groups and you tried to factor one group, you'd see you're not going to get the same binomial in each one. Okay, so factor by grouping is not going to work, which means this could turn out to be really long. So what we do is we look at this 2,000 over here, and we think of the factors of 2,000. Okay, and we have to think of the context of our problem so that we're not doing all kinds of, big extra work. So, I mean, a factor of 2,000 is 2,000, but can the depth be 2,000?
No.
Right, so it's more likely going to be at a small line. You think about when you're talking about a swimming pool. I mean, 1,000 is also a factor, but are you going to have a swimming pool that's 1,000 feet deep?
No.
No. So we're going to start at the low end. Is it likely to be 1,
No.
2? Okay, 3 is not a factor of 2,000, so we skip over 3. 4?
No.
Maybe. All right. So, yeah, you guys have been in pools that are 4 feet deep, right? No? Okay. Okay. What will we do to check real quickly?
Plug it in.
Plug it in and check. So we could do synthetic division with it, or you could actually plug it in. Those numbers are going to be kind of big. I would probably do synthetic division. It turns out it's not 4. Also, you could plug in here. If it were 4, that would be 4. This would be 9. This would be 39. Sorry, I lost track of what I was doing. Okay, if we multiplied those together, would we end up with 2,000? No. Okay, then we move on. 5, and turns out 5 is the one that works. So 5, that would be 10. This would be 40. If you multiply those 3 together, do we end up with 2,000? Okay. All right, so did we start with a problem that looked like it was going to be really gross and unmanageable? In many ways we did, but in the end, it was not so bad. Yes?
Okay, so with problems like this, if the grouping doesn't work, is that kind of guess and check, or we just find the factor?
No, well, we know that a factor would have to be it would have to be made up of a factor of 2,000 of that last term, and so we just started running through numbers. Right, and you could go through and check. I would do synthetic division on this. I would not try the factor theorem just because the numbers are going to be so big. But if you quickly threw in 5, right, into that 140, would it be negative or positive?
Sorry.
Yeah, 175 and 2000. Yeah, we'd figure out really quickly that we get the 0 here. And so we would know that would be one of them. Okay. Yeah, and again, I would rather do the synthetic on this than try to plug 5 into this long thing because those are some pretty big numbers. All right. How are we feeling overall?